So did you check yesterday this SN1 and SN2?
Oh, no, I didn't
You
find time.
didn't
Yes.
find time. Okay, fine. May I know
I
your
trust
schedule?
the entire morning. So can you revise that then,
Yeah,
SN1?
of course. Today class will be that only, because of
Okay.
course that is the part of this haloalkanes and haloarenes. But if you
So
have
how many class would we take more?
see the remaining part like this SN1 and SN2, E1 and E2, these two
Hmm.
will require at least two classes. Okay,
Huh.
the two
Huh.
classes. Then rest is free radical or electrophilic substitution are there. So maybe 2 or 3 classes I can wind up. So maximum I will try to wind up in 5 class, next 5 class. I will
Hmm.
try to wind up. Okay.
So 4 to 5 classes, you're saying?
Yeah, 4 to 5 class. I'll try to wind up.
Okay,
And
cool.
later on, we will discuss some problems based on the board exams
I
or board
also have one
NCRT
more thing.
problems. Yeah.
Can you send some questions as well?
Yeah. Of course, today we'll discuss a few problems because until now we have not studied, we have not entered into the concept now. Until now we have
No, no,
not.
some questions to practice at home as well.
Yeah. Today, like from today class only, we will enter into the real Haloalkane and Haloarene. Until now, it was like introduction part only and some remembering part only. It has nothing new. Like 2 or 3 reactions were there. You need to remember from preparation of alcohol. Just 3 reactions were there. Then
Hmm.
this Finkelstein's reaction, Swire reaction, that is a straightforward reaction from PCl5, PCl3. Just that is not a big issue. Directly you can solve. But conceptual part from it will start from today. Okay. So
Okay.
we will start with SN1 and SN2. See the types of reaction. Basically, this is chemical properties. Okay, last few class as we discussed, we have discussed like preparation of haloalkanes, and we discussed 2 or 3 methods. Can you recall them? What all the 2 or 3 methods which we discussed? One was from directly from
So
alkane.
PCl5, PCl3.
Yeah, directly from alkane. First we prepared from alkane. Just try to recall it.
So using from alkene using H nu.
Yeah, using H mu. So that was useful for preparation of what? Chloride, bromide, fluoride,
No.
iodide, which one?
Haloalkane, huh?
No, which
And
one?
then after that we
But
studied.
we use this H mu and heat that was
Hmm.
beneficial for like preparation of chloride, bromide, iodide, fluoride. That was the
Chloride and bromide,
yeah,
right?
fluoride and bromide. Okay, fine. Then we
So
dis
basically, chlorine and bromine are mostly like a pair, right? Generally.
yeah. It is like a pair. Yeah.
Hmm.
Okay. Then we
So
discussed.
iodine and bromine
Yeah,
use
it was not possible.
method.
Yeah, that was reversible reaction and it has a high electronegativity, so it was not possible. Then we
Hmm.
discussed with alkene. And in
Alkene we use Markovnikov
yeah, in
rule.
alkene we used Markovnikov rule, anti-Markovnikov rule, but
But
anti-Markov
it's also called Kharash rule, right?
yeah, it is also called Kharas rule. Yeah.
Yeah.
Okay, so and anti-Markovnikov in the presence of peroxide, it will follow anti-Markovnikov rule, and that is
Hmm.
applicable only for what? HBr, not HCl.
Hmm. Only HBr.
Yeah, only
Only HBr in the presence of H2O2.
yeah, H2O2 or peroxide, any peroxide we can use. Okay,
Okay.
okay, fine.
Okay.
Then we discuss with alcohol, preparation from alcohol. And from preparation of alcohol, we had Lucas reagent, CONC-HCl plus
Lucas concentrated
anhydrous
HCl,
ZnCl2.
ZnCl2.
Yeah, then we discussed with and one property was there with the Lucas reagent. Which one will give the fastest result? 3 degree, 2 degree, or 1 degree?
3 degree, 2 degree, and 1 degree.
Yeah, 3 degree will give the fastest result. Turbidity will come immediately. Then 2 degree it will come from within 5 to 10 minutes, and 1
Hmm.
degree it will not give in at room
1 degree it
temperature.
won't come in room temperature.
Yeah,
And
we have to heat it for some time, then it will give the product. Okay, fine.
what
Then
about for 0 degree? For 0 degree?
0 degree, of course, the same process only, na?
Oh, same
Yeah,
process.
it's the same process only. Okay.
Okay.
Then we discussed preparation
Using
from
PCl5, PCl3.
PCl5 and PCl3. So the product was different for both the reaction. You need to remember the product. The first one was
Okay.
what? With the PCl5, like POCl3 was there and the HCl was there.
Uh, uh,
Okay, RCl plus
uh,
POCl3 and HCl. Okay.
uh, uh.
Then plus H2O, sorry, not HCl, H2O was there. Then with this one, PCl3, we get
Wait,
H3PO3.
PCl5 is HCl only, no?
Yeah, HCl, yeah,
Okay.
HCl.
No, I think you said H2.
Okay. Then this one with PCl3,
With PCl3, we get H3PO4, no?
H3PO4, yeah.
No.
So these two you remember, RCl plus
Yeah.
H3PO3. Okay.
Hmm.
Then we discussed again with the best
You
method
had
of,
mentioned that was the SN2 type of
yeah,
reaction, no?
SN2 type of reaction. Today we will discuss what is SN2
Today
and
we
SN1.
discussed.
Okay. Then we prepared using
SOCl2,
SOCl2.
Darjan's method.
Yeah, that was called Darjan's method, and that is one of the best method for preparation. Why it was the best method? Because the product was the gaseous
Are
mixture.
gaseous. The
Yeah,
product are
so
gaseous and it's a pure
it
product.
is a pure product. Yeah, so directly we can remove the gases,
Okay.
all the byproduct, and we will get the best product in that. Okay.
Right.
Then we
Hmm.
discussed halogen exchange method. So the
Hmm.
halogen exchange method was used for preparation of two halide like iodide and fluoride. Previously we
Huh.
were not able to make iodide, but from the Finkelstein reaction we can prepare alkyl iodide. Okay, Rx plus
So what
Na,
is the acetone formula again? Acetone formula?
acetone CH3CO CH3.
CH3CO. Huh. C
Acetonic,
double bond O. C.
acetonic
Huh.
CH3, C double bond O, and
CH3.
CH3. This is
Ketone.
acetone.
Huh.
Yeah,
Ketone group.
yeah, it is ketonic group. Okay,
Okay.
so from
Okay.
this one we prepared alkyl iodide. Okay,
Hmm.
and the reaction name was Finkelstein reaction.
Equals time. Hmm.
Yeah, then 1 minute,
So no reverse is possible in this.
1 minute. Yeah, so in this one no reversible reaction was there. Then
Huh.
we discussed later on which one more reaction was there, Schwarz reaction.
Swartz. Hmm.
Schwarz reaction. So that was useful for the preparation of alkyl fluoride.
Fluorine.
Okay, and what was the reagent? AgF, Hg2F2,
Or
Hg,
Hg2F2. What is
yeah,
Hgf2 called? Hg
Hgf2 mercuric fluoride, you can say.
mercury fluoride.
Yeah,
Or SbF3, no?
yeah, SbF3. Yeah, just remember the reagent, no need to remember the common name. Okay,
Okay.
okay, fine. So today we will see the chemical properties of alkyl halides. Okay, this was all about preparation. Now we will see chemical properties. So this class is important. Chemical properties of alkyl halides. So chemical properties, we will see two or three types of reaction. One is SN1 reaction, SN1. Another is SN2, then E1.
So what is the
E2.
essence of SN1 and SN2? What does it mean?
Yeah, I'll tell you. First, note down these things. What type of reaction we will see? SN1, SN2, E1, E2, and one more mechanism is there, E1 CB mechanism. Okay, we will see one by one all the what all the reaction is. Okay, so
Huh.
basically what is happening here? Suppose there is one nucleophile here. Nucleophile. Do you know the meaning of nucleophile? Any species which is
Huh.
electron rich, that is called
Electron
nucleophile.
rich.
Yeah, and
So
we
this is the electron loving species. Huh?
not electron loving species, electron rich species. Electron
No, so
loving species is,
nucleophile and electrophile, right?
yeah, electrophile. Electrophile is electron loving species,
Okay,
and
okay. I
nucleophile is,
always get confused between electrophile and nucleophile.
see, whenever you have deficiency of electron, then that
Huh?
will be electrophile. Deficiency of electron means there will be one positive charge. So it has some deficiency of electron. So that is deficiency of electron. Then to compensate this electron, they will love electron so that the electron will be compensated. That's why
Hmm.
this carbocation or electrophile are known as electron loving species. Okay, but
Hmm.
nucleophile, they have excess of electron. This excess of electron can be used for preparation of sigma bond. That's why these are called electron rich species. There is difference between electron loving species and electron rich species. These are electron rich species.
Electron rich.
So remember this one. These are electron rich species. So what will
Huh.
happen here when we will react nucleophile with some alkyl halide? Okay, this R is there and L is some leaving group. So what will happen? This nucleophile, this lone pair of electron is there. This has excess of electron. This excess of electron can be used to prepare one sigma bond, and simultaneously what will happen? Leaving group will leave from this alkyl group. So what will happen? We will have one formation of sigma bond between nucleophile and alkyl group. So from these two electrons we have formed one sigma bond. Okay, and leaving
Huh.
group has left from this alkyl group, and we have got here one negative charge. Why this negative charge? Because this electron has been transferred on this leaving group.
Hmm.
Okay, got it?
Okay. Hmm. Got it.
Okay, so this R can be anything. This R is a substrate. So what are the factors? See, this is the basic reaction, and we'll discuss like what all the factors and how it will, like when it will break, initially it will break or simultaneously it will break. We will discuss one by one, but initially we will see what is this R or alkyl group. Okay, so what are the
Hmm.
factors which it will depend? Okay, so first factors, on which it will depend is number 1, that is R. And what is R? R is the substrate,
The alkyl group,
the
right?
alkyl group or alkyl group.
Substrate or alkyl group.
Okay, fine.
Okay.
So this can be either anything, either it can be a methyl group, or it can be ethyl group, C2H5, or it can be isopropyl group. Got it? Here one more
Hmm.
hydrogen will be there, or it can be tertiary butyl group, CH3, CH3, CH3. This group will be there, or it can be even vinylic also, CH2 double bond, CH2. This is vinyl, or it can be allyl. Remember what is allyl? CH2 double bond means anything which is adjacent to the carbon atom or double bond.
Lilac and vinylic is
Yeah. So this is what? This is vinyl. This is vinyl and this is allyl. Remember? Or
wait, what is vinyl and allyl? I think I'm missing it. Wait.
okay, no problem. Just you can recall it once. Allylic means a carbon atom or any functional group.
Okay. We had written
Okay. So
allylic
this position,
halides and
yeah.
vinylic
So this
halides.
position is called, like, if I will give one, if I left from one here, so I can put one halogen here. So this position is what? This position is allylic. So I will not write this functional group, exact functional group. Just we just write one dash here. Okay. So that will
Hmm.
sign that that is one group. Okay. Another form
Hmm.
can be phenylic, one benzene ring. So that is phenylic, or it can be even benzylic. Benzylic
Benzyl.
means like one CH2 group will be here. So this one is benzylic and this one is phenyl. So one is phenyl and this one is benzyl. So there can be any substrate. Okay, we can use any of this for given substrate from here. And
Hmm.
another one is the leaving group. Okay, so this one is substrate and second one is nucleophile. Nucleophile. So what is difference between nucleophile and base? Do you know any difference between what is nucleophile and what is base? So basically just write this difference of nucleophile. Nucleophile are those particles which can donate an electron and they can generate sigma bond by donating this electron pair. Okay. So nucleophile are those particles, those not particles or molecules, or those molecules which can donate electron pair to generate sigma bond. To generate sigma bond. Here you can say, see, this nucleophile was present here, and what it has done, we can just donate its lone pair here, and we have
Hmm.
generated one sigma bond here. So this is called nucleophile. Okay. So how it will happen here? Just take one example. The same example we can take here. So here there is one nucleophile here, plus one substrate is there. Suppose one RCl is there. This lone pair can be used to generate sigma bond. So what we will do, we will generate one sigma bond between what? Nucleophile and this alkyl group, and from
Hmm.
here this leaving group will leave from here and it will form negative charge because electron has been accepted by this molecule. Okay.
Hmm.
There one difference between base also behaves in the same manner, but it is little bit different from the nucleophile. So what are bases? Because these two will come together, nucleophile and base will come together every time. So bases, what are bases? Do you know the basic difference between base, acid and base?
Basically, dissociate to form OH minus and H plus.
Yeah. H plus, they will form H plus acid, and bases will form OH
OH
minus.
minus.
Okay, fine. But bases have one more property, that they can abstract one proton also. OH minus, what it will do? OH minus, basically it will accept one proton. So
Hmm.
anything which can accept one proton, that is also called base. Okay.
And acid can give that one proton.
Acid will give that H plus and base will accept that H plus. Okay. So this
Hmm.
one, write this definition for base. Bases are those molecules which can abstract
Hmm.
a proton in a solution. So how it will abstract? Suppose we will see this one. If B, I am denoting base by a B, okay, B minus. So here also one negative charge is there, on nucleophile also one lone pair is there, and what is doing here, it is donating one electron. So what it is doing here, HCl suppose I take, so here also the same sigma bond is formed here, same sigma bond, then BH, okay, plus Cl minus. So here we can see that reaction is somewhat similar. Here also this electron is used for generate one sigma bond. Here also this negative charge lone pair is used to generate sigma bond. Got it? Can you see that similarity here? The similarity is both have generated one sigma bond. Here also one sigma bond, here also one sigma bond. But the only difference between the base and nucleophile is that this nucleophile will form sigma bond with any of the alkyl group, okay? But base will always extract hydrogen only. Always extract hydrogen. This hydrogen is important. So when this sigma bond is formed between the hydrogen, then that is called base. If it is the sigma bond is formed other than hydrogen, that is called nucleophile. Got it? So you can say that all bases are nucleophile, but all nucleophile are not bases. You can see from here, because here also sigma bond is generated and bond is formed. Here also sigma bond is generated, bond is formed. Here bond is formed between alkyl group. Here a bond is formed between only and only hydrogen. Means all bases are nucleophile. Write a note here. All bases are nucleophile, but all nucleophile are not bases. Got the difference? All nucleophile are not bases. Okay, so we will see this reaction. Basically we will study this reaction only, how it is proceeded or how it is converted into this product. Okay, so there are two types. The first type is SN1 reaction. SN1 reaction. So we will see one by one what is this SN1, SN2 and all those things. So nucleophilic substitution. So nucleophilic substitution of the first order. So right here.
So SN stands for nucleophilic substitution.
Yeah, SN. N means nucleophilic, S means substitution, nucleophilic substitution, 1 means first order. Nucleophilic substitution of first order. So what is happening here? The basic reaction is the same, nucleophile plus R L. Nucleophile is donating its electron and it is forming one sigma bond with alkyl group, and one leaving group is left from here. Okay, so what is possible pathway? First we should see the terminology. What is this terminology here? Already we have discussed. R is here substrate. Substrate can be anything. Then here L means leaving group. Leaving group can be anything, chlorine, bromine, iodine. L can be anything, any halogens. Okay, then third one is Nu. Nu means nucleophile, anything which are lone pair of electron, like H2O. H2O, it has also one lone pair of electrons, so this can also act as a nucleophile. Okay, or CH3OH, this can also act as a nucleophile. Okay, and the fourth property will be some solvent effect. We will see solvent. So solvent can be of two types, either it can be polar protic or aprotic. We will discuss later on. Okay, so solvent effect will also be there. So what are the possible pathways or mechanism? Possible pathways. So here what has happened here, again I am repeating, one sigma bond is formed between alkyl group and leaving group has been left from this molecule. So possible pathway, what has happened here in the first step, this is important. First step, this leaving group was there, this RL, it has left initially in the first step only, and this is the slowest step, and the slowest step is called rate determining step or RDS. This step is the first step and slow step, and that slow step is called rate determining step. and this is the only which is govern the rate of the reaction. Okay, so what will happen here? Just tell me, if we break this bond from here, then what will happen here, right?
R plus and L minus.
Yeah, exactly, R plus and L minus. So slowly and slowly you are able to understand now the charges. Okay, so this R plus, what is this R plus? Now positive charge is here. What is this called?
It has lost an electron, a
Lost an
cation.
electron, and it has formed a carbocation.
Carbocation.
So once carbocation is formed, then you have to apply the same concept which you apply on every carbocation. Means you have to apply the stability order, you have to apply the rearrangement possibility, everything you have to apply here. Got it? Okay, this is the first step. Once carbocation is formed here, then in this second step, what will happen? This carbocation is there, R plus, then it will combine with what? This nucleophile. It will donate its electron here and Nu, or I will write in this way, like R is here. So this R and Nu. There is no charge on R, because once it has gained electron, then there should have been a negative charge on R. But it has one already positive charge, so negative and positive charge has been cancelled out. Got it? And this nucleophile, like it has already one negative charge, I am using this excess electron, so it has already one negative charge nucleophile. So this negative charge means 2 electrons are there, so these 2 electrons has been used to make a sigma bond. So this reaction has been completed in 2 steps. First step is what? Initially one bond is broken from the leaving group and carbocation is formed. In the second step, this nucleophile has formed sigma bond with this alkyl group or carbocation. This one is the rate determining step or slowest step. So this is the one pathway, and this is called SN1 reaction. So what are the characteristics for this reaction? Why I have written in 2 steps? So we will see the characteristics. Until now you have written?
True.
Okay. So we will see the characteristics for this reaction. So the characteristics, how much time? 8:53. Characteristics. So first one, the rate. So the rate is like, have you studied the kinetics?
No, we haven't done chemical kinetics.
Okay, no problem. So see, this is the what all the means reagents here. One nucleophile was there plus RL was there. Okay.
So that's the concentration, right?
Yeah. So this is, if we write in the bracket, then that is the concentration. So what are the reactants? In the reactant, this one is there and this one is there. Okay. So I have written in this one, I have used only this part of the reactant, and I have here written here power to the power 1. So whatever the power here, that is the order. Okay. So I have used only this one, not this one. So this rate will depend only on this substrate, means alkyl halide group, and that is the power 1, means nucleophilic substitution of the first order. Then this is the first order reaction. So the rate will be directly proportional to only on this one, leaving group. The rate will not be dependent, like whatever the factor you write here, the rate will depend on those factors. So you can see here, I have not written here nucleophile. Can you see? Nucleophile was present in the reactant, but I have not used in the rate law. Means this rate will never depend on.
What is L in this case? L was
leaving group.
So leaving group, as in, can you give some? Okay, yeah, basically halogens and all. Okay.
CH3Cl. It can be this one.
Yeah, so halogens.
Yeah, any halogen. Okay. CH3Cl, anything. CH2Br.
No, why are they called leaving groups? Because they
leaving group means because they will take one electron and leave from the substance. Like you see, because that is electronegative atoms. Okay. So they want electrons so that they can get saturated or they can get stable. So what they will do, from some or the other source, they will try to extract one electron and they will go from anywhere. Okay. So they will take from this electron and they will leave from this compound, and they will be happy by accepting the electron. So that's why they leave the molecule. That's why they call leaving group, and they leave the compound very easily, because there will be leaving effect from other, like there will be some oxygen, they will not leave easily, but halogen will leave easily. So any molecule which leave the molecule, we call it leaving group. Got it? So the halogens are best among these. Okay. So this rate is not dependent on nucleophile. So it is independent of nucleophile. So irrespective of any nucleophile you take, whether you take weak nucleophile, you take a strong nucleophile, the rate will not depend on those nucleophile. Rate will depend only on the substrate. First part, which you need to remember.
Only on the substrate.
Yeah, only on the substrate.
Okay, and what was K? K was the?
K is the rate constant.
Rate constant.
K is the rate
This
constant.
is
We
in
will
chemical kinetics.
yeah, it is the part of chemical kinetics.
Okay, we
Okay,
haven't done
we'll
this.
study again in chemical kinetics. Okay, just
Okay.
remember this part. Rate is directly proportional to this one, subtract, and the power 1 means first order reaction. K is the rate constant for this reaction. Okay, then order. What will be the order? Then again we will study in the chemical kinetics that whatever the power for this one, that will be the order. So here the power is 1 means order is 1. So that's why it is called SN1, means nucleophilic substitution of the first order. Okay, you can write it again, nucleophilic substitution of the first order. Therefore it is called SN1 reaction. Shall I write it again, nucleophilic substitution of the first order?
All right,
No need.
of the first order.
Okay,
Okay,
fine.
got it.
Then again we can see the first step. First step was what? The carbocation was formed here. Rl means R plus L minus. Then carbocation was formed here. Okay, so the rate will be directly proportional to stability of the carbocation. This is also one very important. The rate is directly proportional. Rate of reaction is directly proportional to stability of carbocation. Okay, so suppose I take 4 examples here. Example, so what will be the rate for this reaction? From here I can see CH3Cl. suppose I take this substrate, or CH3 CH2Cl, or CH3 Cl CH3, and then hydrogen CH3 CH3, and again CH3 and Cl. So first, what will happen in the first step? One chlorine will move from here, one chlorine will move from here, this chlorine will move from here, this chlorine will move from here. Every time this chlorine minus will be formed, and on substrate what will happen? This positive charge will come here, again positive charge will come here, again positive charge will come here, again positive charge will be come here. So what do you think? Which one will be more stable carbocation? 1, 2, 3, or 4?
The most stable one would be
This is
1.
3 degree, this is 2 degree, this is 1
Then
degree.
4, 3, 2, 1,
So
right?
do you still have any problem to identify what is 3 degree, what is 1 degree?
No, so why did you say it was 3 degree again? Just as one carbon left. This carbon,
This,
principal carbon
yeah,
is
this is the reference molecule. This
huh.
carbon is,
The principal carbon is connected to 3 other
yeah,
carbons,
3
so 3
other
degree.
carbons. So that is why it is 3 degree. This carbon, this is the reference atom. Then this reference atom is attached to this carbon, and this carbon is attached to 2 other carbon, means 2 degree. This is the reference atom. This reference atom is attached to one carbon.
So it's called the alpha carbon, right?
Yeah, it is called alpha carbon.
Alpha carbon.
Okay, got it. So alpha carbon will be this one, not
So the
this one.
number of carbons which it is attached to determines the stability.
Yeah, stability. So not number of carbon, carbocation, because positive charge will be formed here, na. Okay, so
So
positive
number
charge.
of carbons attached to the carbocation.
Yeah, number of carbon. So stability is not due to carbon, stability is due to hydrogen. Because what is happening here, this positive charge, already I have explained this one, again I am telling you. This is positive charge, means it is excess of electron or deficiency of electron. Positive charge means
Deficiency.
of co-deficiency. So what it will want? It will try to lose more electron, it will try to gain electron.
Gain.
It will try to gain electron. So hydrogen can donate electron through you can hyperconjugation. You might have studied, I don't know whether you have studied or not in your GOC. Hyperconjugation, mesomeric effect, inductive effect. Have you studied these things in your 11th?
I think, yeah, I'm familiar of the
You are
terms.
familiar. Okay, so this
Hyperconjugation.
electron can be donated from this hydrogen atom. Remember this fact. So here there are total 9 hydrogen, 3 from here, 3 from here, 3 from here. So total 9 hydrogen is donating electron to this carbocation, means this is more stable. But here only 6 hydrogen is donating. This is not donating because this is directly attached. Only we have to consider
So the directly attached one does not donate.
director. We have to see the alpha part. This is alpha carbon and this is
Alpha
alpha
carbon.
hydrogen. So here 6 hydrogen is donating electron to this person. Okay, so here it
So
is,
the carbons attached to the alpha hydrogen are beta.
yeah, see, this
Right.
is positive charge, this is carbon, and this is hydrogen. So this is
So what is the hydrogen called? Is it alpha hydrogen
this
there?
is called alpha hydrogen. Yeah, exactly. This is called alpha hydrogen. So how
Then
many?
what about the hydrogen which is directly attached? What is that called?
That is not called anything. That is
Oh.
directly attached to the one atom only. Just adjacent one is called alpha hydrogen. Okay.
Hmm.
Then adjacent to adjacent is called beta, and then
Hmm.
adjacent to adjacent is called gamma. Okay.
Hmm.
So suppose if I add here one more carbon, then that will be beta. If I add one more carbon, then that will be gamma. Okay.
Hmm.
Reference
Oh.
one is which one? Reference one is this atom.
Hmm.
Okay. So here
Okay.
there is 3 atoms, means 3 degree. 3 degree carbocation is more stable. Just remember this thing: 3 degree carbocation is more stable than 2 degree, then 1 degree, then 0 degree. At least I have repeated maybe 3 to 4 times for sure, that 3 degree carbocation. So what I have said here, the rate is directly proportional to stability of carbocation. So which one SN1 reaction rate will be faster? So the rate will be faster. Rate will be faster for 4. Rate of SN1 reaction. So rate on one SN1 will be fastest will be for 4, then it will be for 3, then it will be for 2, and it will be for 1. Got it or not?
Got it.
Got it? Okay. Try one more question. For which one SN1 will be faster? SN1 rate. Predict SN1 rate. So suppose I take 2 examples. Simple one. CS3Br and CS3 CS2 and CS3, and here CH, not CH only, and Br. For which one rate will be faster? 1 or 2? SN1. I am talking about
So
SN1.
in this case, the carbon is attached to two other carbons, so two and then one.
Yeah. So this one will be rate will be faster.
Hmm.
Okay, got it?
Got it.
Fine. Then one problem is that whenever carbocation is formed, then you have to remember that rearrangement is also possible.
Hmm.
Okay. So this was the third point. This is the fourth point. Rearrangement. Rearrangement of carbocation is possible. Okay, suppose
Hmm.
I take this example. I am not writing hydrogen part here. I am just writing carbon part. Okay. So suppose here one chlorine is there. Okay. Now what will happen? Once chlorine will move from here, then what will happen? In the first step, one positive charge will be formed here. See, and then here positive charge will be formed here. Got it? Then this positive charge will not remain here. This is 1 degree carbon. But if positive charge will come here, then it will be 2 degree carbon, because this positive charge will be attached with this one and this one. Can you see this fact? This is 2
Hmm.
degree.
Hmm.
But
Hmm.
again this can move from here. How many hydrogen will be there? That many times it can shift. Okay. Even
Hmm.
methyl shift can also be there. Phenyl shift can also be there. So here also it can shift from here. Okay. So here
Hmm.
this positive charge will come here. So that is called shifting of positive charge. So you have to
Hmm.
remember this one. This is very less possibility that it will be asked in your 12th class. But you have to remember this thing that
This is J level.
yeah, JE level it will be 100%. You can't ignore each and every question will be on rearrangement of carbocation only. Okay, they will not ask it.
Wait, wait. So I didn't exactly understand. So the which one shifts the hydrogen?
Yeah, this positive charge. See,
The carbocation
yeah,
charge.
carbocation. See what will happen here. Just see here. Here
Hmm.
hydrogen is here present.
Hmm.
Hydrogen, this positive charge is here. Okay. So what
Hmm.
will happen here? This hydrogen can donate electron to this person. Okay. So what will happen? CC, and this hydrogen will shift here. Okay. Hydrogen. Sorry, there are 3 carbons. So I am writing one more carbon here. So 1 2 3, this hydrogen has came on this carbon because it has donated this electron from here, but this carbon has lost one bond from here. That's why positive charge will come here. Got it?
Hmm.
So just move one hydrogen and write one positive charge. I will tell you, I can tell you from here, one positive charge is there, then hydrogen is here. Okay. Then what will
Hmm.
happen? This hydrogen will shift here and positive charge will shift here. You can shift this positive charge from here. So I will directly write here. So what will happen? I am just rubbing this part from here. and this here, this one, then hydrogen will come here, and this person has lost one bond, so positive charge will come here. Okay, so this from 1 degree it has become 2 degree. Can you see 2 degree, one carbon here, one carbon here? Okay, but again it can shift from here. This hydrogen can also donate here. Got it? So again what will happen, this positive charge will come here and hydrogen will move there. So this hydrogen will move here, hydrogen, and positive charge will come here. So what will happen here, like this is now 3 degree, 1 2 and 3. Got it? So whatever the nucleophile is about to come, this nucleophile will come on this carbon. So nucleophile, whenever this nucleophile will be there, so it will come on this carbon. So nucleophile will get attached on this carbon, not on this carbon. That's why I am telling you rearrangement of carbocation is possible. Will you able to remember this one? This is highly important. Okay, they will not ask tough question on this one, but you need to remember the rearrangement part.
It's basically just a part of the question.
Yeah, it is the part of the question. Okay, so rearrangement of carbocation is possible. So this is one aspect. Okay, so solvent effect. Solvent effect I will not tell you in detail, but there are two types of solvent. Solvent effect, fifth part. Solvent, then there are two type of solvent, one is polar protic and one is aprotic. Okay, so the solvent used here will be polar protic solvent. Polar protic solvent. So anything which donate protons like H2O, anything which can donate one proton, that is called polar protic solvent. Got it? So like H2O will be polar protic, or CH3OH will be polar protic, or C2H5OH will be polar protic. Got it? Phenol will be polar protic solvent. So anything which can donate H plus, that is called polar protic solvent. So this reaction is favorable in polar protic solvent. Okay, you need to remember this one. Okay, fine. Then we have to see what one, the nucleophilic effect. Okay, nucleophile strength, nucleophile or leaving group effect. Leaving group. So leaving group can be anything. Suppose one chloride is there, bromide is there. So like Rx I am telling about. So one can be Rf, another can be RCl, another can be RBr, another can be Ri. Okay, all will leave and can be leaving group. Do you know, you have any problem in this one? This fluorine can also leave, chlorine can also leave, bromine can also leave.
We discussed this. No, L stood for leaving group.
Yeah, L stood for leaving group, and for leaving group it can be either fluorine, chlorine, bromine, iodine. But which one will be better leaving group among these four? Okay.
So the most reactive one would be fluorine.
It's it is not based on reactivity. Okay. See what is happening here, one carbon is there and one halogen is attached here. Okay. This halogen is can be anything, either fluorine, chlorine, bromine, iodine. So in whatever the case this bond is broken easily, then in that manner X minus is leaving easily. So we have to see among which of the following this bond will be broken easily. Okay, this is the funda here. Okay, so here you see the size of carbon, and here you see the size of other atom. Okay, so the carbon and iodine size is a lot of difference. Okay, so suppose like if you are wearing some sandal and your size of the sandal is like 5 or 6. Okay, and if I will make you wear a sandal size of like 10 or 12, so what will happen? It will easily go away from your feet. But if I will make you wear a sandal size of the same size of your feet, then it will remain intact in your feet. Can you feel this one? So the size of carbon is very much difference between the size of iodine. Iodine size is somewhat larger. Like if you go from top to bottom,
iodine has a lot of protons, right? It has a very large mass.
Yeah, it has a large size. Okay, so due to the large size, it's not able to form bond in effective manner with this carbon, because both have very difference in the size. Okay, carbon is very small size and iodine is larger in the size. What is this rule? So of course when size difference is there, so this bond will be broken easily. This carbon and iodine bond will be broken easily, but due to the difference in similarity of size, carbon and fluorine bond will not be broken easily, because the size factor will be like this one, then size factor will be this much, then size factor will be this much, and then size factor will be this much. So this size is a lot of difference here with the carbon, so the bond overlap is not that much favorable. So that's why this bond is broken easily. So the iodine will move more easily than fluorine. So which one will be better leaving group? Like Ri will be better leaving group. Okay. So if you see the rate of the reaction between Rf and Ri, which one will have higher rate? So Ri will have higher rate, because it will be broken easily. Okay. Okay, got it?
Got it.
Yeah. Now the 7th part. This is also important, the stereochemistry. Stereochemistry. So stereochemistry means, have you studied R configuration, S configuration? Okay, first you need to see what is chiral atom. Stereochemistry, I will give you just basic part.
Which cannot be superimposed.
Yeah, chiral atom. What is chiral atom? If any carbon atom is having all 4 substituent different, X, Y, Z and B, all 4 atoms are different, that is called chiral. Okay, that is called chiral. And if we invert this molecule, like suppose I am writing this one, carbon X and Y, Z and B, and here also I am writing X and here Z, and I have inverted this position. Y I have written here and B I have written here. So what is this? This is mirror image. Okay, so this is mirror image. So if this configuration is R, this configuration will be S. You know that the configuration, what is R configuration, S configuration? If you don't know this configuration, just remember that these two molecules are different. This is different molecule, this will show different optical property in stereochemistry, or I will
Optical isomerism, right?
yeah, optical isomerism. Okay, so these two are different compound, because see, this Y is different here, and this Y is from left hand right hand side, this Y is in left hand side. So these two have molecular formula are same, but they have different structure formula, so they are optical isomers. Okay, these are isomers, and they are called known as optical isomer.
Optical
Okay,
isomers.
until now it is okay.
Okay.
So and these two are different molecules. Okay, and they will show optical activity. Optical activity means, if you take any plane polarized light, if you take this molecule, you take plane polarized light, okay, and you pass plane polarized from this molecule, so it will turn into this direction for R. But if you take this molecule, then if you pass plane polarized right, then it will pass into this direction, left. So that is S. It can turn into right direction, it can turn into left direction, both will turn in different direction. This is what optical activity is if you take plane polarized light, PPL. Until now it is okay. Okay, so why I am discussing here optical activity or stereochemistry? See, one thing is important here. Suppose this molecule is there, like if I take one example on the next page, what was happening here? Suppose I take this example, pH and hydrogen, here chlorine, and here CH3. This is what? This is one leaving group, chlorine. And if I write here one nucleophile, what is H2O, then H2O will form in two directions, pH, CH3. One can be this one, H and OH, and another pH, H and OH and CH3. This OH can come in both the direction, either in this one or in this one. How it has happened here? Because initially what has happened, see, just see this one, pH, H, CH3 and Cl. Initially what has happened here? Initially leaving group has removed from this molecule and one positive charge was formed here. So this is carbon here, this is carbon. So carbon, then pH, then what is here? This is CH3 and this is hydrogen. So this is what? This is a planar molecule and one positive charge is here. So this is planar molecule. This is 3D molecule. This is 3D molecule and this is planar molecule. Do you know the difference between 3D molecule and planar molecule? it is in the same plane. Like this phenyl is on the top of the screen, this hydrogen is the bottom of the screen in the left portion, and this CH3 in the bottom of the screen of the right portion. So this is in the planar molecule, but this is not planar molecule, this is 3D. Like this one will be like in one plane and another will be like this plane. This is in the screen part, like top of the screen and left of the screen, and this is inside the screen and this is outside the screen. Okay, so this is 3D. Got it or not what I am saying? So this is not planar molecule, but this is planar molecule. So whatever the nucleophile is there, it has one possibility that it can come either from this direction or it can come either on this direction. In both way, this nucleophile can attack here. Got it? So if this nucleophile will attack from this direction, then this will be formed. Okay, and if it will attack from this direction, then this will be formed. Got it? So is there any restriction here that how much it can come from this direction or how much it can come from this direction? Is there any restriction you can see here? We can't see any restriction.
No restrictions.
It can come either from this one, and that is probability. What is the probability? This probability is 50-50. So 50% this product will be formed and 50% this product will be formed. Okay, so this one will rotate in the right direction, this is different molecule. This one rotate in the left direction, so overall that will be cancelled. So SN1 reaction will give racemic product. This you have to remember. So racemic product.
R stands for racemic?
No. R does not respect for racemic. Okay. Racemic means there is no optical activity.
Okay.
No optical activity. See, this one will rotate in the right direction, this one rotate in the left direction. But suppose this molecule is present in 50-50 manner. Okay, so 50% will rotate right and 50% will rotate left. So what will be the overall rotation? Overall rotation is 0. So overall rotation is 0 means that compound is not optically active. Optically active means it should rotate at some angle in some direction, either left or right. But here it is not rotating, means it is not optically active, means SN1 reaction give racemic product. This you have to remember. Okay, SN1 reaction note. SN1 reaction gives racemic product. Racemic product means no optical activity. Got it? So what we have learned here? We have learned that initially in the first step, one bond is broken and carbocation is formed. Carbocation means more stable compound, means more stable, means more rate of, so 3 degree will be rate of the reaction will be highest for. So what we have learned here, rate for SN1 3 degree, greater than 2 degree, greater than 1 degree, greater than 0 degree. Okay, this key point you have to remember. And overall product is racemic mixture. Okay, and leaving group, how it will depend, Ri, if Ri is there, then it will be more for RBr, then it will be more for Cl, then it will be more for Rf. Okay, we will solve some example on this one, but first remember these 3 key main points are there.
Ri, RBr, RCl, RF.
Rf. Okay,
Basically descending order from the group.
Okay, so this was the all about this SN1 reaction. Okay, now we will see what is SN2 reaction. SN2 reaction, thing is the same but the process is different. So this is nucleophilic substitution by molecular. First write the definition. Nucleophilic
substitution by molecular.
Means 2 molecules are involved here, by molecular. So here also the same process will be there. One nucleophile will be there, plus one substrate will be there, and one leaving group will be there. Here it will form bond, leaving group will leave from here, nucleophile will bond form with the substrate, and leaving group will come out. Okay, but here the process will not like initially we saw that the first step, this leaving group was removed from here and carbocation was formed. Okay, but here the situation will be somewhat different. Here what will happen, all the process will occur simultaneously. Simultaneously means one nucleophile will come here and it will try to form bond with the substrate, okay, and this leaving group is rigid, it has not left from here. So what will happen, it will again be, there will be some more product here, like this nucleophile and R, this is simultaneously attached with leaving group, okay. Now this leaving group is feeling uncomfortable, this is one like intermediate, okay. Now this leaving group will come out from here and here the product will be formed. So nucleophile and R and plus leaving group. So in the first step of the SN1, this leaving group was left initially, but here this leaving group is not left initially, it has left when this nucleophile has attached here. Got it? So what will be the difference between here and here? So what will be the deciding factor here? Okay. So the first of all we will see the characteristics here. So we will take some basic example here. Suppose one carbon is there and one leaving group is there, and we will substitute three more group. Suppose I substitute here X, and here I am writing in stereochemistry form, and here it is Y, and here it is Z. So what has happened here, nucleophile has came here, nucleophile is trying to form bond with this carbon. So initially what has happened, nucleophile and then carbon, and here X and then Y and then Z. This is one like transition state, we say transition state, and simultaneously this leaving group was there and this leaving group trying to move from here, and that's why from here this nucleophile carbon and then X, Y and Z and plus leaving group, okay. Got it? Now see the characteristics for this reaction. Characteristics of reaction. So the first characteristics is rate equal to K into R into L, that is rate is dependent on the substrate, okay, as well as the rate is dependent on nucleophile also, means this is our power 1, this is power 1. So the overall order is, what is the overall order? Order is equal to, you just add the powers of this reaction, means this rate law. So 1 plus 1, order will be 2. Any problem?
No.
Suppose if you have any substrate here A,
The order is basically
the
the
power of
concentration,
the coefficient,
the power of the concentration, 1 and 2. 1
power.
and 1.
So for this one order will be 4.
3. Okay,
Okay,
including
order
that.
will never be 4, but for this one order will be 4, or if I write here 1, so order will be 3. Just
So
add.
this K is a constant, right? It's a number.
Yeah. See, but when I will teach you this chemical kinetics, then you will understand in better manner. But just remember here, we just
Okay.
add the power of the coefficient. Okay, so order is 2. So 2 means SN2. So this
2.
rate is dependent on both nucleophile and the substrate. In the SN1, this rate was not dependent on the nucleophile. Do you remember? But here this
Uh,
nucleophile will will affect the rate. So
uh,
nucleophilic substitution of the second order. Substitution of nucleophile of second order. See again here for SN1 the nucleophile was independent of the rate. So doesn't matter if you take a strong nucleophile, whether you take weak nucleophile, it doesn't affect the rate because it was independent. But here for SN2, if you will take weak nucleophile, then reaction will be slow. If you will take a strong nucleophile, then reaction will be fast because the rate is dependent on the nucleophile. Okay, is it okay for
uh,
you? So you have take a strong nucleophile here. Okay, so rate is directly proportional. Rate is dependent on concentration and strength. Concentration and strength of nucleophile. Plus, is here carbocation is formed here or not? Can you see any formation of carbocation?
No, right?
No, we don't see any formation of carbocation. So when carbocation is not here, then there will not be any kind of rearrangement. Okay, carbocation rearrangement will be only when there will be formation of carbocation, but here no carbocation is formed, so there will be not rearrangement. So no carbocation formation, hence no rearrangement. Okay, leaving group. So leaving group should be like, there should be leaving group should be better leaving group. So leaving group I am writing in LG group. Okay, leaving group. So leaving group also it will follow the same order, means Ri greater than RBr greater than RCl and greater than RF. So this is all about this leaving group. Got it?
Got it.
Okay. Now we see here the nature of the substrate. So substrate. What is the
So
substrate?
leaving group is the same, right? We
Yeah,
wrote
leaving
last
group is
time.
the same here. Leaving group is the same. So nature of the substrate. Nature of
Substrate.
substrate. So now see here CH3Cl, again I will take this example, CH3 CH2 Cl, then CH2 Cl and CC. I am writing here, I am not writing hydrogen here, should understand.
Got it.
Okay, got it. Now you see here, suppose I take from here. Okay, see this nucleophile is present here, he is trying to make one sigma bond with this carbon. Okay, but there are already some three groups available here, X, Y and Z. Okay, and these three are bulky group. Okay, so if I increase the crowding here, so whether it will be easy for this nucleophile or it will be difficult for nucleophile if I increase the crowding here.
Difficult, right?
Yeah, it will be,
Difficult.
yeah, it will be difficult. Okay, and if I decrease the crowding, then it will be easy. Got
Easy.
it? Yeah, you understand this fact? So if I increase the crowding, then it will be difficult. If I decrease the crowding, then it will be easy, because it is trying to make sigma bond with this molecule. Previously this was not the factor, because carbocation was formed and it was having enough space to form one sigma bond. But here it is adding simultaneously, because already 4 bond is present here, 1 2 3 4, and he is trying to add one extra fifth bond. That's why he has just forcefully entered into this picture, and that's why this fellow has left from here. Got it? If you are sitting one chair and one fellow will directly come and sit on your chair, what you will do? Either you will kick him out or you will only go. Got it? So this fellow has sat on here, that's why this living group has left from here. Now we will come on this one, this example. Okay, now you see which one you can see more crowding here. You can see more crowding in 1 2 3 or 4. Which one you see more crowding, 4 or 1?
4, right?
Yeah, of course. This is 3 degree, this is 2
4
degree,
degree, 1
this is
degree, and
1
0 degree.
degree, and this is 0 degree. So of course this is more crowding because 3 carbon is there. This is less crowding because this hydrogen is there. So hydrogen no problem, this is a smaller molecule, but carbon is bigger molecule, so crowding will be more. So what will be the rate of the reaction? So the rate of the reaction is inversely proportional to the crowding. So rate is inversely proportional to bulkiness of x, y and z. Whatever the x, y and z, if it is more bulky, then rate will be slow. If it is less bulky, then rate will be fast. So in this one the rate will be faster for 0 degree, then 1 degree, then 3 degree. You got this point? Got this point? So what was the rate for the SN1? The rate of SN1 was 3 degree was more, then 2 degree, then 1 degree. Got it? But here the rate has been reversed. For SN2 reaction, the rate is highest for 0 degree, then 1 degree, then 2 degree and 3 degree. Got it?
As it's more crowded,
Yeah,
the
as it
less
is more
crowded one
crowded.
is
Yeah,
easier.
that's why it is difficult. Okay. So, okay. So for 3 for SN2, the rate is rate order for SN2 is equal to 0 degree, 1 degree, 2 degree and 3 degree. It was just reverse for SN1. Okay. Now we see solvent effect. Solvent effect. So solvent effect, use this polar aprotic solvent. Use polar aprotic solvent. This is not important for your board exam, but this is important for your NEET GMAINS. That polar aprotic solvent is used here. Okay, fine. Do you know any example of polar aprotic solvent?
Polar aprotic solvent.
See, anything you can see, DMF, dimethyl formide, DMA, dimethyl acetamide, but this is not important. Just Google anything.
Wait, what about DDL?
Not DDL. What is DDL?
What is DDL?
Not DDL. See, DMSO, one is that dimethyl sulfoxide, DMSO. Okay,
DMS.
dimethyl
What is the full form?
sulfoxide, dimethyl sulfoxide. Then one is DMF. DMF is dimethyl formide. Okay, DMA. DMA is dimethyl acetamide. No need to remember, just remember that we will use aprotic solvent, means hydrogen will not be protonated from here. Okay, this is solvent effect, but most important we have to see the stereochemistry. This is highly important. In SN1, what was the stereochemistry? What we had formed? We had formed racemic mixture. Got it? Why? Because previously carbocation was formed and this nucleophile was independent to attack either from the left or from right. So that's why we got mixture of product, and that was overall racemic mixture. But now see here SN2 stereochemistry. Suppose I am writing from here this chlorine, this CH3, and this is X, or I can write here deuterium. This D is deuterium and H is hydrogen. Now I am writing here SN2, not SN1. So what will happen here? This nucleophile will come here. So what is the possibility of coming of nucleophile? Either in this direction or in this direction. Suppose if you have to kick some person, what is easy to kick, in from the front side or back side?
Backside, right?
Of course, back side. So if it will try to come from this side, then this will not go from here. This will remain sit here. Okay. So what he will do here?
This is a 3D molecule, right?
Yeah,
This
this is
one?
3D molecule. Yeah, of course, this is 3D molecule. So this nucleophile will come from the opposite direction of the living molecule. Okay. So previously what was that? There was one transition state. So transition state, what was the transition state? Suppose I am writing this one. So this is CH3, this is hydrogen, and this is deuterium, and one is chlorine here, which is about to leave here. So this nucleophile will come from this direction. Got it? So this nucleophile will come from this direction. So what will be the product here? So you can see the product here, CH3, and then D, and then what has happened here? This nucleophile was here, then chlorine was here. So this hydrogen will come this direction, and this nucleophile will come in this direction. So what has happened here? From initially the configuration was this one, this configuration has been reversed. Can you see this fact? If this was SN2, then CH3, Cl, deuterium, and SN2. SN2 means, like, if suppose I take any OH nucleophile, so what will happen here? OH will come from this direction, OH, then hydrogen, and then CH3, and then deuterium. So the previously one group was in this direction, in right hand direction, the another group came from backside. That's why this fellow has came here. So if this configuration is R, so this configuration will be S. Then what has happened here? The configuration has been reversed. This is important.
Got it.
Configuration has
been inversed.
reversed in case
Wait, inversed or reversed? Reversed, right?
in case of SN2. and thus reversion is called Walden inversion. This is called Walden inversion. Remember this one, Walden inversion. So if I take the plane polarized light, then this fellow will rotate in the right direction. If this fellow will rotate from right direction, so this fellow will rotate in the left direction. But in case of SN1, this was not the case. We got it the racemic mixture because there was 50-50 probability to attack from either left or from the right. That's why we got it racemic mixture. There is no optical activity. This compound is optically active with the inversion of the configuration. So this is more important. Okay. So what are the favorable factor, favorable condition for SN1? So favorable, sorry, SN2. So favorable condition for SN2. So SN2 means the substrate will be 1 degree substrate. If 1 degree substrate is available, then easily it will go SN2. Okay, good leaving group, polar atomic software, and strong nucleophile. Nucleophile should be strong. Strong nucleophile. If it will not be strong, then it will not be able to kick out from here. Okay, it will not be able to kick chlorine from here. Okay, if it is weak nucleophile, because this is very rigid fellow, and this is not like carbocation has not been formed. But in the SN1, once carbocation was formed, like if any stupid nucleophile will be there, it will go and form the bond. Got it? Got it. Okay. So this was the
Got it.
favorable condition. So now if we see the order, like not order overall, we compare. Okay. So compare for 1 degree. Suppose this is 0 degree, 1 degree, 2 degree, and 3 degree. If we go from 0 degree to 3 degree, then which probability will increase? The probability for SN1 or SN2? If we go from 0 degree to 3 degree, then order of SN1,
It will be 3 degree, 2 degree, 1 degree
SN1
for
will
SN.
increase, because for SN1 3 degree is more favorable because carbocation is formed. So 3 degree is more favorable because more stable carbocation will be formed. So for 3 degree SN1 will be favorable. But if we go from this direction to this direction, then which one will be favored? SN2 will be favored. Got it? SN2 will be favored. Okay. Got it?
Got it.
Okay. Now you see one example here. Suppose I take one example. Compare rate of SN1. Compare rate of SN1. CH3Cl, CH3, CH3 fluorine, and this is CH3 bromine, CH3 iodine. Which one the rate will be faster?
CH3I, CH3B, CH34, F, CH3Cl.
So
No.
this is the rate SN1 rate. Okay. Now again, which one SN1 rate will be faster? CCC 1 chlorine, CCC, 1 minute. This chlorine is here, and CCC, C, and chlorine. Which one will be faster for SN1?
So SN1 only, right?
Yeah, SN1 only.
So the third one is 3 degree. 2 degree and then 1 degree.
1 degree. Okay.
Simple question.
Yeah, yeah, same principle. But one, I will give you one smart question. Okay. Have you studied resonance?
The movement of the negative positive charge, right?
Okay. So for which one the rate of SN1 will be faster? For 1 or 2?
The rate of SN1. So this carbon is sp2, right?
Yeah,
S
yeah. See, both are sp2 only, means 2 degree carbon. Both are 2 degree carbon. So now from this 2 degree we can't predict the answer. But I have told you that SN1 will be favorable for like more stability. More is the stability of carbocation, more is the rate. So carbocation will be formed in both the cases. So one carbocation will be this one with one double bond, and another carbocation will be this one. Which carbocation is more stable, this one or this one?
So I think the first one is more
First
stable.
one is more stable because it is undergoing resonance.
Huh.
This is resonance. Resonance stabilized carbocation. Okay, you have I
Oh
think,
no, if that moves over there, the plus would move. The
yeah,
plus
yeah,
would move to
yeah.
one. No.
Plus will move from here. So what has happened here? This positive charge has shifted from here to here.
Huh.
Means it has increases the stability. So double bond will come here and positive charge will come here. So you can
Huh.
say the simple example that suppose you are carrying a 10 kg bag, okay,
Huh.
but you have
Huh.
one option that 1 kg, that 10 kg bag, either you can shift in right hand, then after 1 minute you can put it in your left hand and you can exchange at your own. Okay, this is one possibility. But another possibility is that you need not have to, like you are not allowed to exchange your hand, you have to carry in one hand only. So in what case you will be more uncomfortable, or in what case you will be comfortable? The bag in which you are exchanging from right hand to left hand, you will feel comfortable. Got it? Got it
Huh.
or
Huh.
not? So this
Huh.
positive
Huh.
charge, this positive charge is moving from here to here. So this positive charge is making unstable, okay, this molecule. But it has
Huh.
one possibility that it can shift positive charge from here. So it is making himself comfortable. Okay. So that's why
Hmm.
this resonance shifting of charge will make compound stable. So this is more stable. So more stable means more stable carbocation, means rate of the reaction will be faster. I think I need 1 or 2 class for GOC for you. Okay, you try
Hmm.
to find one's time. I will take you one
Huh.
or two classes for general organic chemistry. So I will discuss all these examples. What is
We could try Saturday or Sunday then.
yeah, yeah, that will be another, like it will not be related with this haloalkanes or
Hmm.
haloarenes. That will be one
Okay.
separate class. Okay,
Okay.
so that
Okay.
you will not get stuck with these problems. Okay.
Huh. Huh. Huh.
So this was all about this SN1 and SN2. Okay. So what are
Huh.
the key things you have to remember for SN1? 3 degree is more stable 2 degree than 1 degree, and
Huh.
rearrangement of carbocation is possible. Then
Hmm.
substrate Ri, RBER, RCl, and this one. And what is the stereochemistry? Resmization.
Huh.
Okay. For
Huh.
SN2,
That's my concern. Huh.
yeah, for SN2 means like SN1, there is rate is for SN1 rate is dependent only on the substrate for SN1, but for
Huh.
SN2 the rate is dependent both on substrate and the nucleophile. Okay, then
Okay.
the nature of substrate, 0 degree will be more favorable because there is less crowding.
Hmm.
Okay,
0 degrees is
more
favorable. Huh.
favorable because of less crowding. Then inversion will be there because the nucleophile will be attacking from the behind.
Huh.
Okay, got it? So I will try to give some few examples as an assignment to try to solve those before the next class.
Hmm. Okay.
Okay. So
Okay.
when we will have our next class? Tomorrow?
No, not tomorrow.
Then
Maybe Thursday or Friday.
Thursday or Friday. Okay, then let me know.
I'll inform you tomorrow if it's Thursday
Yeah,
or
yeah,
Friday.
yeah, yeah. But for tomorrow you will not have any class. Okay, now.
No, no class tomorrow.
Okay, okay. Then let me know latest by tomorrow, day after tomorrow morning. Okay.
Huh, I'll tell you. I'll tell you tomorrow itself.
Okay, okay, fine. Is it okay for you today's class?
Huh, it was nice.
Yeah, yeah.
So
Okay.
I think we'll go with Friday itself.
So go with Friday.
What time are you free?
Friday I will be free at 7 p.m.
Hmm.
Yeah.
So 7:30.
Yeah, no problem.
Hmm.
Not an issue. Okay,
Okay.
we'll meet on Friday.
All right.
Fine. Thank you.
Thanks.
Thank you.
Bye.